Hello, this is Nicholas. I decided to make a video on parameterization. Parameterization, something like that. And the idea behind parameterization is pretty cool. You'll see it a lot on Mu Alpha Theta tests. I'm mainly making this for my pre-calculus students, but I mean, the idea itself can come in handy pretty cool in pretty interesting ways. So to start off the talk, so curves are one-dimensional, right? So if I on an xy plane, this is your x and this is your y. And I give you this curve. Maybe this curve is e to the x or something. And now realize this curve has no width. I've drawn it and you see it has that little width for you to actually see it, but the actual curve itself just has length. So it would make sense that we'd be able to describe this curve y is equal to f of x. It would make sense to describe it rather than the usual x and y that we have. We usually have an x and y. It would make sense to be able to describe it in terms of just one variable, which you can call theta. In other words, since the curve only has one dimension, we should be able to describe it with only one variable. And that's the kind of clutch of the idea, is that we only have one variable that we're working with. So let's consider a unit circle to begin with. Maybe x squared plus y squared is equal to 1. Now, we can describe the circle with one variable using trigonometry, right? You might recall x is equal to cosine theta. Maybe I should draw it. So circle, radius 1. This x distance here is cosine theta. That y distance there is sine theta. So y is equal to sine theta. Now, so if I let x be sine theta, or if I let x be cosine theta and I let y be sine theta, theta is going to range from 0 to pi over 2, so we trace out an entire circle. And now realize that this still is this, this and letting it be this are the exact same thing, because, cosine squared theta plus sine squared theta is equal to 1. And so the dummy variable theta, and you could have used any variable you want, that is what's known as the parameter. Okay, and the parametric description that we have is useful not only because it has only one variable theta, but also because theta is unconstrained. In other words, it can take on any value that we would like it to. Right? Sine and cosine are continuous. But in our original xy descriptions, right here, only certain pairs of xy are on the unit circle, right? But in this particular case, theta can be whatever we want it to be. Okay? But only, right, like if I put x be like 5 million or something, At least I don't think there's any y that would that you could plug in and still get 1. Well, no, there wouldn't be. See, like, if you let x be equal to 5, I'm just gonna say 500. Okay. That point cannot exist on the unit circle here because there's no number y such that 500 squared plus y squared is equal to 1 when we are well, technically there is, but when we're considering y being a real number. That's what that symbol means. Y is an element of the reals. Okay. So now let's try a more complicated circle. X minus 5 squared plus y minus 3 squared is equal to 16. Now you may have learned this, you may have not, but so this circle is centered at 5, comma 3. In other words, the 0 of these two expressions here. It has a radius of the square root of 16, or 4. Just like how this one had a radius of the square root of 1, or 1. So we want to find a pair of functions. X is equal to f of theta, and y is equal to g of theta, such that those two functions describe the above circle. They describe this circle here. Now realize that if we write x is equal to 5 plus f of theta, y is equal to 3, maybe I should have wrote f sub 1 of theta, plus, and then y is 3 plus g sub 1 of theta, because it's a different function. It's not our original f of theta, it's a different one, so that's why I have the subscript there. Then, where did my pen go? Oh, there it is. Okay. Then what we're gonna get is, okay, I guess I should write it out just for this first time. We're gonna get 5 plus f sub 1 of theta minus 5 quantity squared plus 3 plus g sub 1 of theta minus 3 quantity squared is equal to 16. Or in other words, f sub 1 of theta squared plus g sub 1 of theta squared is equal to 16. And you see how we use this here? Well, this is like this formula here for our circle, x squared plus y squared is equal to 1, is awfully suggestive of this formula here, right? They look really similar. Here we've just got f sub 1 of theta plus g sub 1 of theta, and is equal, and instead of x and y. In other words, we parameterized the function, so it's just in terms of one variable, which we let theta be our dummy variable. So, what am I going to do? I'm gonna let x be equal to 5 plus 4 cosine theta, and I'm gonna let y be equal to 3 plus 4 sine theta. And when you plug that in, when you plug it into here, right, you're gonna get The 5s and the 5s are going to cancel out. You're going to get 4 cosine theta squared plus 4 sine theta squared is equal to 16. In other words, 16 times cosine squared theta plus sine squared theta is equal to 16. And I got that because I'm squaring both the 4 and the cosine theta. And then I'm pulling it up front as a constant. And now this is equal to 1. And obviously 16 is equal to 16. So what that tells you is that this here is our parametric function, or a parametric representation of our new circle. So a couple things also went on there that I wanted to mention. See, basically what's gonna kind of happen is you're gonna want to be using your Pythagorean identities from trigonometry, right? I realize here that I have something squared plus a different something squared is equal to 16. And so you want to make those somethings be other things in terms of theta, and you want to use your Pythagorean identities to kind of get that to be true. In other words, like, I know, for example, in the unit circle, right, I knew cosine squared theta plus sine squared theta is equal to 1, so I made use of that, and I just wrote the whole thing in terms of theta. Here, right, I know, like, I can't just let x minus 5 be cosine theta, because then I'm going to get cosine squared theta, and then I can't just let y minus 3 be sine squared theta, because then I'm going to get cosine squared theta plus sine squared theta is equal to 16, but it's not, it's equal to 1, right? So that's why you have these 4s here, right? You kind of have to maybe think a little backwards in your head. That's why I put those 4s there, because I knew when I squared 4, I got 16. And if I put that out front, then I would have this true relationship there. And again, I wanted my constants, my 5, my negative 5, and my 5 to cancel out, so I just had this cosine theta, this 4 cosine theta. Right? You want it to be as simple as possible. So that's why I added a 5 to that negative 5. And the same logic for this term here. Okay. So I'm gonna do one more example, but basically the idea is you kind of want to make these equations, at least when they're describing like conic sections, like circles or parabolas or hyperbolas or ellipses or stuff like that. You kind of want to use your Pythagorean identities. That's kind of what's kind of going on in the back in these sort of problems. So another example is we want to I'm just going to say parametric description instead of parameterized because I can't spell it, of the line 2x plus 3y is equal to 5. Okay? I want to solve this for y, I like it better in that form. So y is equal to negative 2/3 x plus 5/3. So okay, there are many possible parametric representations that we can use to for this function here, but usually the simplest of examples is to just let x be equal to t, and then y be equal to negative 2/3 t plus 5/3. So in other words, t is x, so x is t. Nothing really crazy going on over there. Also, sometimes and you're probably thinking, well, what's the point of doing this? The point of doing this is that now you have it in terms of just this t. It's really, in this particular example, it isn't all that useful to do this, but if you have like a degree 2, like with our circles, that's a lot more useful, when dealing with those functions. One that is slightly more challenging is, where'd my pen go? Okay. So I'm going to try to spell it this time. Parametrize the following function: 9x squared minus 4y squared minus 72x plus 16y plus 164 is equal to 0. This equation, and we haven't learned it yet, but this equation describes what is known as a conic section. In other words, a cross-section of a conic, right? So you imagine like slicing it with a plane. And I'm a horrible drawer, but wow, let me maybe redraw that just a little bit better. And you can look them up. I don't really like them that much because it's just a bunch of formulas really. But imagine this is your plane and you're kind of slicing at an angle, all right? So the cross section created by this plane is this elongated circle if we're going at an angle. It's an elongated circle and it's known as an ellipse. Okay. And basically, I don't want to make a video on conics, but basically your circle equation is x minus h squared plus y minus k squared is equal to r squared. Yeah. And so hopefully, in other words, okay, now what you're gonna do is you're gonna okay, in an ellipse, right, an ellipse is like an oval. You can think of it like an oval. And so if this is your center here, you've got a shorter axis, right, like here, and then a longer axis along here that pass through your center point. And what you can do is you can let this longer length be A and this shorter length be B. And it turns out its area is equal to pi times A times B. In other words, the area of an ellipse. And a way that always made sense to me was if you've got a circle here, its area, right? We've got R and we've got R. They're the same. In an ellipse, you either stretch it out this way, right? Or maybe you'll stretch it out that way. But in other words, one axis, like this line or this line, one is longer than the other. But for a circle, the area is pi times R times R, pi r squared. Here in an ellipse, it's the same thing. You're just making one axis one side longer and then shortening the other. Right? That's how I've always remembered it. Anyway, why did I do all that? Okay, so with an ellipse, basically what you're gonna do is you're gonna let R be equal to AB. And you're gonna divide. This is gonna be over A squared. This is going to be over B squared. And this is technically going to be over A squared B squared. But since R is equal to AB, R squared is equal to A squared b squared. So that just becomes 1. And that's your general equation for an ellipse, x minus h squared plus y minus k squared. X minus h squared over a squared plus y minus k squared over b squared is equal to 1. I feel like I did a poor job on explaining that, but I'm gonna, there'll be another video on conic sections. That wasn't the whole purpose of this video. Okay, back to this. So basically I did all that because I want to get my original equation, since I know that it describes, I want to get this original equation over here, looking something like that, because that looks a lot nicer than this whole big foiled out mess over here. So what I'm going to do is I'm going to kind of put my x and y variables together. I'm going to get 9x squared minus 72x, and I'm going to leave a little bit of a space, minus 4y squared. Do I want to leave a space just yet? I don't think I do. Oops, my eraser got so big for a second. 72x plus 16y plus 164. Minus 72x minus 4y squared plus 16y is equal to negative 164. Now I'm basically like gonna complete the square for each one of these separate polynomials in x and y. So in this first one here that I've underlined, I'm going to pull out a 9. You get 9 times x squared minus 8x. And now I'm going to add 1/2 b squared. That's kind of for completing the square, that's what you use, completing the square. So, and b is your middle term here in your polynomial. So, a half of b is 4, negative 4 really, and then you're squaring it and you're going to get 16. Now, we have minus 4 times, and I pulled out a minus 4 instead of a positive 4 because I like positive leading coefficients, and you should too. They work out nicer. So y squared minus 4y plus 4, using the 1/2 e, right? You pulled your 4 out, so this coefficient becomes a 4, and then you divide that by 2, you get 2, and then you square it, and you get 4. And this is negative 164. But now, since I added these, I have to do the same on the right side, right? If I add something to one side, I have to do the same thing to the other side. So now realize here, we didn't actually just add 16. We added 16. Oops, I wrote a 19. We added 16 times 9. Because there's a 9 out front. We're multiplying this 16 by a 9 and then adding that if we were to like foil this all out. And so 16 times 9 ends up being 144, because 16 times 10 is 160. Subtract a 16 here, 144. So since I added that over there, I have to add it over here. And now, right here, I really added a 4 times negative 4, or negative 16. So in other words, I subtracted a 16 over here as well. Now I'm going to get 9 times x minus 4 squared, right? I take the square root of this, take the sine of this, and I take the square root of this. Minus 4 times y minus 2 squared is equal to, well, this is minus 20. Minus 16 is minus 36. So, minus 36. Now, this actually works out nicely, but basically, see in this over here, I didn't have coefficients, so I don't want coefficients down here either. So what I'm going to do is I'm going to divide by the product of my two coefficients. In other words, I'm going to divide by negative 36. And that's usually what you're going to be doing when you're simplifying these sort of expressions. Now, ooh, what happened to my pen? Okay, it keeps going away. I'm going to get, I'm going to write this term in first because it's going to be positive. I'm going to get y minus 2 squared over 9 minus x minus 4 squared over 4 is equal to 1. And that actually turns out to be a hyperbola. Basically, here we had a plus sign. When we make it a minus sign, it becomes a hyperbola. And I will do a proof for that later on. It's pretty messy, though. A hyperbola, if you don't know, kind of looks something like this. You've got like something like this, and the hyperbola kind of asymptotes along. It always has asymptotes, and it kind of along those two diagonal lines. It looks something like that. Anyway, I'll go into all that stuff later. Now, okay, in our previous, we're left with this now. In our previous example, where we had x squared plus y squared is equal to 1, it made sense to use the identity sine squared theta plus cosine squared theta is equal to 1. But here, we have something squared minus something squared is equal to 1. So we're going to have to be using one of the other two Pythagorean identities, namely 1 plus tangent squared theta is equal to secant squared theta, or cotangent squared theta plus 1 is equal to cosecant squared theta. Now I want to, what do I want to do? Well, you could actually use both. See, I want to solve these for 1. In other words, I want to make it either secant squared theta minus tan squared theta is equal to 1, or cosecant squared theta minus cotangent squared theta is equal to 1. So actually, either one of these identities you could make use of. I guess I'm going to make use of this one first because I don't really like this one as much. So, basically, I'm going to let y minus 2 squared over 9 be equal to secant squared theta, and x minus 4 squared over 4 be equal to tangent squared theta. So, what now? Now I just want to solve for x and y in that. So, this one I'm going to take the square root of all of these. So we get y minus 2 over 3 is equal to secant theta. And over here we get x minus 4 over 2 is equal to tan theta. So x is equal to 2 tan theta plus 4, and y is equal to 3 secant theta plus 2. And that is one parametric description of the function that works. I guess since I'm making a video on it, I might as well. I'm a little full. Let me just kind of make some room. There we go. Okay. I didn't really erase anything important. This is still our equation we're going to use, but I'm just going to use this identity now. And you'll see that functions have multiple parametric representations. This is kind of the point of why I'm doing it. So now, in this particular time, I'm going to let y minus 2 squared over 9 be equal to cosecant squared theta, or x minus 4 squared over 4 equal to cotangent squared theta. So y minus 2 over 3 is equal to cosecant theta, and x minus 4 over 2 is equal to cotangent theta. So y is equal to 3 cosecant theta plus 2, and x is equal to 2 cotangent theta plus 4. So that representation, that parametric representation, is also equally valid as before. Both of them work. So, it doesn't really matter which one you use here. Perhaps since I talked about ellipses, let's find a general parametric representation for an ellipse. And an ellipse, if you recall, is given by the equation x minus h squared over a squared plus y minus k squared over b squared is equal to 1. And just kind of as a recap here, this is an ellipse. It's got its longer axis A. A, and its shorter axis B. And this point, in other words, HK is your vertex. And yeah, that's about all I want to tell you all for now. So I want to find a general parametric representation of this. So I have something squared plus something else squared is equal to 1. Now I know my Pythagorean identity, cosine squared theta plus sine squared theta is equal to 1. So x minus h squared over a squared, I'm going to let that be cosine squared theta. Because when I let that be so, and then when I let y minus k squared over b squared be equal to sine squared theta, I'm going to get cosine squared theta plus sine squared theta is equal to 1, which is a true relationship, which means the parameterization is valid. Okay. And so again, just usual stuff here, taking the square root. And then this. So our general parametric representation is x is equal to a cosine theta plus h, y is equal to b sine theta plus k. And so if you actually substituted this in for y, you would after all the algebra, you'd get that 1 is equal to 1. So you knew your parametric representation is valid. Okay. Now I wanted to move kind of on to the opposite. In other words, undoing this stuff. So it's important to find parametric representations for curves, but it's also important to determine the original equation for the curve when you're given the parametric equations that describe it. And this is, what is it called? Sometimes they'll call it like reducing the parameter, or eliminating. Let's just say eliminating the parameter. So you might see it called that on Mu Alpha Theta tests, or you might say, or they might say, find, they might give you a parametrized function, and then they'll say, make this into Cartesian form where you've got an x and y, or they might say eliminate the parameter. Just realize that it's all the same thing. So let's say I give you x is equal to 3 plus log of t squared. And just for a moment here, if you see log of t squared, whenever you don't see a base on a log on your on your mu test or whatever, assume the base is 10. Okay? In other words, log base 10 of t squared, or 10 raised to what power? 10 raised to what power? That's a question mark. Gives me t squared. Okay, and let's say I give you y is equal to 2 minus log t, and I want you to find an equation of a curve satisfying the parametric equations. And notice how I said find the equation of a curve, because you have multiple curves. So see, here I have a log of t, here I have a log of t squared. If you remember from your log properties, I can take this exponent here and put it out front as a coefficient. So I'm going to get x is equal to 3 plus 2 log t. And again, y is equal to 2 minus log t. Now basically this is just a linear equation, so to say. We're just going to combine our equations to eliminate t, to eliminate the parameter, and just substitute one equation into the other. So let me do this. I'm gonna make this 2y is equal to 4 minus 2 log t. And the reason why I did that is because I'm gonna add these. I'm gonna get x plus 2y is equal to 7. And because those are going to go away, right? I want those t's to go away. That's what it means to eliminate the parameter. This t is gone, that t is gone. They're gone. So, and that is our desired function in Cartesian form. There's no parameter, there's no t or theta or whatever dummy variable you use. And, sometimes they might want you to solve it for y. And, you'd solve it for y, you get y is equal to 7 minus x all over 2. However you want to do it. But, in other words, that's the idea there. And when we have trigonometric functions of parameters, we will just use, multiple identities to get rid of the parameters. That's gonna kind of be what's going on there. Like, if they gave, I don't know, if they gave you sine squared theta plus cosine squared theta is equal to 1. Well, that wouldn't... If they gave you x is equal to sine theta, they gave you y is equal to... Oh, x is never equal to sine theta. X is... y is equal to sine theta. X is equal to cosine theta. And they said, get rid of that parameter there. Get rid of this theta, like how we got rid of this t here. One way you could do it is you could square both of those. Y squared plus x squared is equal to sine squared theta plus cosine squared theta is equal to 1. So x squared plus y squared is equal to 1. And that's kind of the general process. We used this trigonometric identity in that particular case, and they're usually more complicated than that, but in other words, that's the idea, is you're just using a bunch of trig identities. Now, so let's do a little slightly more complicated one. Let's say x is equal to cosine of t minus sine t, and y is equal to sine of 2t, and we want to get rid of this t. Now, there is no real systematic way of going about this. It kind of requires some ingenuity. Realize that... How do I put it here? If okay, I'm going to square this x, basically. X squared is equal to... I'm going to get cosine squared t minus 2 sine t cosine t plus sine squared t. Now, realize also y is also equal to 2 sine theta, or no, I'm using t now, 2 sine t cosine t. So, now cosine squared t plus sine squared t is 1, so get those away and I'll just write 1, and 2 sine t cosine t is sine 2t, so we get 1 minus 2 sine t, sine 2t, 1 minus sine 2t, my bad. Okay, that's x, and then y is just sine 2t. So, and x squared is this. So if I add these, I get x squared plus y is equal to 1. So that's a parabola, right? Y is equal to 1 minus x squared. That's a parabola. Described in terms of theta by here. So, why did I square it? Basically because I knew what sine of 2t was, and I knew if I squared this, I would get a sine of 2t. And just like how here, where I use log properties to get my t's to cancel when I, add or subtracted my equations, that's basically what you're doing when you're eliminating the parameter. You're kind of fooling with x and y. You're doing whatever operations you need to do, so that when you add, subtract your equations or multiply, whatever, your t's are going to cancel. Okay, that's basically what's going on. And I think just one last one here, and then I'll be done. So, so let's say, maybe I should do a new page. Okay. So I want you to find the curve by, well, not you, because I'm going to be doing it, but find the curve described by x is equal to sine squared theta over cosine theta, and y is equal to cosine theta. Okay. So, right away I know that, this is my simplest term. If you remember from, our early example, where it really didn't seem to make, all that much use, but it actually did lead up to this. I gave you 2x plus 3y is equal to 5, and I want you to parameterize that. And so I said y is equal to negative 2/3 x plus 5/3. So a parametric representation of that is x is equal to t, and then y is equal to negative 2/3, and then replace x with t plus 5/3. So basically, I replaced x with something simple and then just wrote y in terms of x. Now, here I noticed that y is, simpler, right? Cosine theta, that expression, cosine theta, looks simpler than sine squared theta over cosine theta. So basically, I'm going to want to rewrite this x in terms of my y, my simpler expression. I want to write my complicated expression in terms of, the simpler expression that I'm given, and then just substitute that simpler expression in to my more complicated expression. So basically, I want to rewrite this in terms of only cosine theta, so that I can just replace that with y, and then be done. So how can I do that? I know x is equal to 1 minus cosine squared theta, over cosine theta, which is 1 minus y squared over y. And that is it. That is your, they might call it rectangular. That's another word they might use instead of eliminating the parameter. That is your rectangular representation of this parameterized curve. I hope that this video was of some help to you. And if you have any questions about anything that I've said, if you're watching this and you know me in person, then I would love to talk about parameterization. There's probably some good problems online. Actually, wait, I might have a cool problem I can leave with you all. Let's see. I got all these problems from my Art of Problem Solving book. Okay. My problem, if you if any of you all are watching this far, here's my problem for you. Find a parametric representation of the line through 1, 2, 3 and -2, -1, -3. And this is actually in 3D. See, we've got an x, we've got a y, and we've got a z coordinate. So your space, right, instead of being just a 2D plane, it's actually like a 3D field. We've got like our x-axis like pointing at us, like our y-axis right and left, and then our z-axis up and down. So yeah, find a parametric representation of the line, so it's linear, so you're not really Cartesian, because Cartesian is only in a plane, but in your 3D plane, so to say, representation, you want to find first the equation of that line in your 3D space, and then from there you want to parameterize it. And if you all have any questions on that one, you can comment on that too, and I love to talk about it. It'd be interesting. Anyway, I think we're done.